Hello everyone, welcome back. We will now have our second lecture on the second law of thermodynamics. Recall from our first lecture on the mathematical statement of the second law of thermodynamics, such that for all processes, the total delta S should be greater than or equal to 0. So the limit is, for all reversible processes, the total delta S should be equal to 0. And for all irreversible processes, the total entropy change should be greater than 0. Okay. So recall that this total entropy change should be the entropy change of the system plus entropy change of your surroundings. From the mathematical statement of the second law, this means that entropy is never conserved but rather always is generated. So another way to write delta S total for any system is entropy generation, or SGen. And SGen is just delta S total, which is calculated by obtaining the change in entropy of your system plus change in entropy of your surroundings. So the change in entropy of your surroundings now is equal to the Q of the surroundings divided by the temperature of your surroundings, T sigma. However, with respect to the system, Q of the surroundings is equal to negative Q of your system. So now if we have multiple surroundings, you just need to take the sum of all the negative Q over T sigma of all the surroundings of your system. Okay. So the total entropy generation for closed systems is equal to delta S system plus summation of negative Q over T surroundings. Now for ideal gases, the entropy change for ideal gases is a function of the change in temperature and the change in pressure as well, with using this expression. Okay. So recall that Cpig over R may be a function of temperature. So some function of temperature is A plus Bt plus Ct squared plus dt raised to negative 2. So usually for iterative calculations, you can expand the integral as follows, and you will get entropy change for ideal gases to be this whole expression. Let us now proceed to the entropy generation calculations for flow processes. So for flow processes, the rate of entropy generation is divided into three terms. The first term represents the rate of change in entropy of your flow streams. So naka-delta S notation, delta SM notation tayo. So it is the summation of all m dot S out minus summation of all m dot S in. Plus, the second term represents the rate of entropy accumulation inside your control volume. The last term is the rate of entropy change with respect to time of your surroundings. And this is now equal to the rate of entropy generation of your system plus your surroundings, which should always be greater than or equal to 0. Again, equals to 0 if you have a purely reversible process. To simplify this further, the rate of change of entropy with respect to time of the surroundings is simply equal to the heat rate of your surroundings divided by T sigma. Tapos naka-negative sign na lang kasi yung Q natin with respect to the system. Substituting, you will now get this expression for the entropy change for flow processes. We can now make further simplifications for steady flow processes. Okay, assume that there is no rate of entropy accumulation inside your control volume. So cancel na si dms over dt. And limiting, or for some cases, for single entry and single exit systems, and in specific entropy units, you will get the following. So delta S minus summation of Q over T sigma is equal to entropy generation, which should always be greater than or equal to 0 once again. So now for flow processes, for you to have a completely reversible process, you must satisfy two conditions. The first condition is on internal reversibility, where your process or a change in your system should be completely reversible. And the second one is called external reversibility, where the heat transfer with the control volume and your surroundings should also be reversible. So there are cases that you will have external reversibility. One example for that is if your process has no heat transfer, your process is adiabatic. However, you can have an adiabatic but non-isentropic process. So if you have an adiabatic non-isentropic process, it means that you satisfy the external reversibility, but you do not satisfy internal reversibility. So if you satisfy both, you will have an adiabatic and isentropic process, or adiabatic reversible process, and that is an isentropic process. Since now we are dealing with open systems and many flow processes usually involve either work producing processes or work requiring processes. So for work requiring processes, the ideal work is defined as the minimum amount of work that should be expended for it to accomplish a particular change in state. For work producing processes, for the same change in state, there should be an absolute maximum of work that should be able to obtain. And in both of these cases, this will happen when the process is both internally reversible and externally reversible. And as such, for these ideal processes, the ideal work is obtained if you have a completely reversible process. Therefore, for completely reversible processes, okay, change in entropy of your flow streams minus Q over T sigma should be equal to 0. Therefore, heat loss should be equal to T sigma times delta S of your flow streams. Now, how do we relate this reversible process to any actual process? So for using the energy balance for steady flow open systems as follows, and we have for a reversible process, Q dot is equal to T sigma delta Sm, and then W will be the ideal work. Now we can make a few assumptions. Assuming negligible Ke and Pe, we can cancel this. Okay. And we can now simplify this further. Okay, so this negligible Ke and Pe change is usually applicable for most chemical processes. And isolating for the ideal work, so the ideal work is equal to the change in enthalpy of for the flow streams minus T sigma delta S of your flow streams. And simplifying for a unit mass of fluid going in and out of our system, the ideal work per unit mass is equal to the specific enthalpy change minus the temperature of the surroundings times the specific entropy change. However, this completely reversible process is only hypothetical and is only used to determine the ideal work associated with the given change in state. Our objective now is to compare the actual work of any process with the work of the hypothetical reversible process. And with this, we define again the efficiency of either a work-producing process or a work-requiring process. So for a work-producing process, the efficiency is equal to the actual work divided by the ideal work. And for work-requiring processes, the efficiency is the ideal work divided by the actual work. And the difference between this ideal work and the actual work is known as your lost work. So the lost work is defined as the actual work minus the ideal work. And this is valid for either work-producing processes or work-requiring processes. So now let's try to develop a relationship between the three. So your actual work rate from our open systems energy balance equation is as follows. And based on the ideal work rate, okay, Q is equal to T sigma delta S of your flow streams, okay, and Ws is replaced by W ideal. And using these two equations, subtract mo lang, okay, this minus this to get an expression for your loss work. So combining the two previous equations, you now get an expression for the loss work, which is equal to T sigma delta S of your flow streams minus the heat loss. So using this, you obtain this from the first law of thermodynamics. So let's now try to use the second law of thermodynamics for open systems. And the second law of thermodynamics for open systems, okay, for a single surrounding temperature is as follows. So delta S minus Q dot over T sigma is equal to the rate of entropy generation. Okay. Now, as you can see here, we can try to obtain an expression similar to this by multiplying both sides of this second expression by T sigma. So you get T sigma delta S of your flow stream minus Q is equal to T sigma times the rate of entropy generation. And using this, we can now relate the magnitude of the lost work with the magnitude of your entropy generation. Thus, the rate of entropy generation is now proportional to the rate of work loss in your overall process. And since the rate of entropy generation is always greater than zero, dapat work loss should always be positive as well. Okay? And as you can see, the greater the irreversibility of the process, the higher is your rate of entropy generation, thus the higher the amount of work loss that you will have. So you will now have less work available, okay, or more of the work that you will need to put into your process to achieve the same change in state. With this, let's now proceed to the second law analysis of steady flow equipment, in particular the definition of their isentropic efficiencies. So our first case will be the operation of an actual turbine. So for steam turbines, usually our assumptions will be adiabatic and negligible kinetic energy and potential energy. So kung adiabatic, we won't have any heat loss, so we will have external reversibility. However, internal reversibility is still up to debate. And from our energy balance, okay, Ws, the shaft work, is equal to m dot times H2 minus H1. Ngayon, how do we get the maximum work for this steam turbine? Okay, so for the maximum or reversible work, dapat delta S should be equal to 0. So if delta S is equal to 0, we are assured of external reversibility since adiabatic in process. So with internal reversibility, the entropy of the inlet and outlet streams should now be equal for you to achieve a full reversible process. Okay? So for reversible work or isentropic work, Ws isentropics is defined as delta Hs, okay? Where delta Hs corresponds to the maximum amount of work, which corresponds to equal entropies of your inlet and your outlet streams. Okay, so for reversible work, it's represented by Ws or delta Hs. Okay, and the condition should be the entropy of state 2 should be equal to entropy of state 1. So S denoted by S2 prime. Ayan. So for this process, for turbines or expansion, consider the HS diagram. The isentropic process is represented by a simple vertical line from state 1 to state 2. Okay? And the actual ideal delta H, okay, this ito si H1, and ito si H2 prime. Okay? Where H2 prime is the enthalpy at this particular specific entropy, which is equal to S1. Okay. Now, from this, we can see that the reversible process represents the maximum amount of work that we can obtain from a turbine. Now, in reality, okay, delta S should always be greater than or equal to 0. Okay. So, ibig sabihin, Ws isentropic should be greater than Ws actual. So Ws actual is equal to the actual H2 minus H1. Now, for any process that is irreversible in an HS diagram, the process will always go to the right. Okay? Never to the left kasi pag to the left yan, pansin nyo, from S1, S2 natin is less than S1. So magiging delta S is less than 0, which should not be possible. Okay, so in this case, consider this path. So ito yung actual path ng process natin. Yan. So towards greater entropy change. Lagi. So to the right lagi. And this is now actual H2. And as you can see, actual H2 value is greater than the ideal H2 value. Therefore, delta H actual is less than delta H ng ideal process natin. Okay. And this delta H2 minus H1 corresponds to the actual work of our process. Okay. So we can now define the thermal efficiency, which is Ws over Ws isentropic or the thermal efficiency, is equal to delta H over delta Hs, which is also equal to H2 minus H1 divided by H2 prime minus H1. Okay. And typically, the isentropic efficiencies of turbines are between the values of 0.7 to 0.8. Okay, so syempre, opposite naman ng turbines natin are your compressors. For compressors, we can make the same assumptions. So assuming adiabatic, so pag adiabatic na yan, we guarantee external reversibility since we have no heat transfer to our surroundings, and negligible kinetic energy and potential energy. So the shaft work is equal to m dot h2 minus h1, and for unit mass, Ws is equal to h2 minus h1. Now, to get the minimum work for a compressor, the reversible work is defined as, again, delta Hs, okay, where S2 prime should be equal to S1. So dapat equal yung entropy ng inlet and outlet streams. And this delta Hs is defined as H2 prime minus H1, okay, where H2 prime corresponds to the specific enthalpy at this particular specific entropy. Okay, so ang assumption dito, they will achieve the same change in state. Okay, so if we now take a look again at the HS diagram, so baliktad naman yung process natin. Okay, so from state 1, we want to compress this to state 2 at this P2. Okay, so to achieve the same change in pressure, so pag isentropic process, again, vertical line lang pataas. Okay, so ito si H2 prime. Ayan. So ito ngayon si delta Hs. However, for our irreversible process, ang nangyayari ngayon, to the right na yung process natin kasi towards increasing entropy. And this value of H2 is greater than the value of H2 prime. So, pakikita natin, as long as you move to the right, okay, lumalaki yung value ng enthalpy na lumalabas sa compressor to achieve the same change in state. Meaning, you will need to input more energy para lang ma-achieve yung same change in pressure. Okay, so, kabaliktaran ito ngayon nung nangyari sa isang steam turbine. So, with this delta H actual is equal to H2 minus H1. So, for compressors, H2 should be greater than H2 prime. Okay. So, ayan. So, S2 prime should be equal to S1. And definition now of the isentropic efficiency for compressors is the isentropic work divided by the actual work. Okay, since the isentropic work, okay, delta Hs, okay, is all greater than, less than, or equal to the actual delta H. And this isentropic efficiency is defined as H2 prime minus H1 all over H2 minus H1. So, ito yung isentropic efficiency ng isang compressor. Pansin nyo, baliktad yung definition niya compared to your turbines. Okay? So, typically, yung isentropic efficiency ng most compressors, again, fall between 0.7 and 0.8. So, to better illustrate this, let's consider this example. You have a steam turbine with a rated capacity of 56,400 kilowatts, which operates at inlet conditions of 8,600 kPa and 500 degrees Celsius, and discharges this into a condenser at a pressure of 10 kPa. Assuming the turbine efficiency is 75%, determine the state of the steam at the discharge and the mass flow rate of steam, given the following steam table values. Okay, so, given sa atin, ang complete inlet conditions, so given si P1, okay na rin si T1. Therefore, we can now get H1 and S1. Now, for the outlet conditions, given lang sa atin si P2, which is 10 kPa. So, we have no other link aside from the given thermal efficiency, which is 0.75. Okay? And again, the definition of the thermal efficiency of a steam turbine or any work-producing equipment is simply equal to the actual work divided by the ideal work. Okay? So with this, gagamitin natin ngayon yung definition ng isentropic efficiency and the reversible process in order to get the conditions of our actual process. So we will now use the reversible work to start our calculations. And to obtain the reversible work, it's used kapag the turbine operates at constant entropy. So for constant entropy, S1 should be equal to S2 prime. Okay, so for the reversible work, this is now equal to 6.6858 kilojoules per kilogram Kelvin. Okay? Meron tayong isang condition, tapos alam natin P2 is equal to 10 kPa regardless kung reversible or irreversible yung process natin. So we now have 2 points. We can now look at the steam table para malaman kung ano yung state ng reversible outlet natin. Okay? And at 10 kPa, okay, this isentropic case, S2 prime, will fall between the saturated liquid entropy and saturated vapor entropy at 10 kPa. So using this, pwede natin makuha ngayon yung state ng reversible outlet case natin. So we can now calculate the isentropic state of the turbine outlet. S2 prime is equal to, again, 6.6858 is equal to yung linear mixing formula natin kapag meron tayong mixture of saturated liquid and saturated vapor. And we can now get the state of the turbine outlet, okay, for the isentropic case, which is 80.47% mixture of liquid and vapor. So it has a quality of 80.47%. Okay. And using this, we can calculate the enthalpy. Okay, again, using the mixing formula for saturated liquid and vapor mixtures, you can now get the isentropic enthalpy outlet of your turbine, which is the following. And using this, we can now calculate the reversible specific work. So the reversible specific work, delta Hs or Ws isentropic, is equal to H2 prime minus H1. And you can now get the following value, which is negative 1,274.15 kilojoules per kilogram. So this now represents the maximum amount of work that we can extract from this process. Okay, so for this process from 8,600 kPa and 500 degrees Celsius, pag in-expand mo yung steam to 10 kPa, ito yung maximum amount of energy na pwede mo makuha. Nothing more. Yeah. So once we have calculated the reversible work, okay, and the reversible outlet, you can now use the isentropic efficiency definition to get the actual outlet of our steam turbine. So the thermal efficiency is equal to delta H over delta Hs, and delta H is equal to this isentropic efficiency times delta Hs. Okay? Or thermal efficiency of a steam turbine is H2 minus H1, the actual, divided by H2 prime minus H1, which is the reversible or the ideal. So H2 minus H1 is equal to 0.75 times negative 1274.15. Or you can also use this. And 0.75 is equal to H2 minus H1 over H2 prime minus H1. And from here, you can now calculate the actual H2, which is 2435.99. And as you can see, H2 is greater than H2 prime. Okay, meaning delta H actual is less than delta H isentropic or delta H ideal. From that, we can now calculate the actual state of the turbine outlet, and if you look at the steam table, it will still fall between the saturated liquid and vapor, specific enthalpies, pero ngayon, mas mataas na yung steam quality natin, which is now 93.78%. Now, to get the mass flow rate of steam, okay, based on the energy balance expression, m dot times H2 minus H1 is equal to W dot actual. Okay, and ang W dot actual natin is negative 56,400 kilowatts. And we have already calculated for H2 and H1, leaving us with m dot. So get mass flow rate of steam, W dot is equal to m dot times H2 minus H1. And substitute the following, you can now get the actual mass flow rate of steam, which is now 59.02 kilograms per second. Okay, so let's now consider another example. This time, compression of saturated steam from 100 kPa to now 300 kPa. If the compressor efficiency is 0.75, what is the required work and what are the properties of the outlet steam? Okay, give it the following steam table values. Okay, so to start your calculations, you should always read first the specific enthalpy and entropy of a stream that has complete given. And in this case, sa inlet, kompleto ang DOF natin. P1 is 100 kPa. Okay, saturated steam. And it is compressed until P2, which is 300 kPa. The only thing else we know about the process is that it has an isentropic efficiency of 0.75. Okay, so complete yung initial conditions, you can read H1 and S1 steam table. Pero alam lang natin sa outlet ay P2, desired compressor outlet pressure natin is 300 kPa. So similar to our calculations earlier from the steam turbine, gagamitin natin ngayon yung thermal efficiency, the isentropic efficiency to determine the reversible work or the reversible state. And using that definition, we can now get the actual state of the process. Okay, so use the reversible work to start calculations, and the reversible work is obtained if the turbine operates at constant entropy. So meaning S1 is equal to S2 prime. So this is now also equal to S2 prime. So kunin natin yung state ng reversible outlet conditions. So at 300 kPa, tignan natin ngayon, okay, and this 7.3598 at 300 kPa falls between 200 and 225 degrees Celsius. So, calculate natin ngayon kung ano yung CT2 prime and CH2 prime. So, interpolate this value and interpolate for this value using this. So, calculating for the isentropic state of your compressor outlet, you will now get T2 prime and H2 prime. And you can now calculate for the reversible specific work, which is equal to H2 prime minus H1, which is equal to WS ideal. Okay? Or also equal to delta H S or delta H ng isentropic process. Okay, which is now equal to 213.37 kilojoules per kilogram. So ngayon, nakalculate na natin yung reversible case. Let us now use the isentropic efficiency definition to calculate the actual outlet conditions. And recall, thermal efficiency natin is 0.75, which is equal to delta H S over delta H actual, which is equal to H2 prime minus H1 all over H2 minus H1. H1, alam na natin, H2 prime, okay now, which is 2888.77. And we can now calculate for H2. Okay, as follows. So H2 is now 2959.89. And again, similar to the case of turbine, H2 is greater than H2 prime. Okay. So ngayon, ano yung temperature ng outlet stream natin? Okay. And ano yung total change in entropy? So reading from a steam table, pansin nyo, interpolate natin ito ngayon, and the actual state of the outlet is now between 225 and 250 degrees Celsius. And syempre, tataas yung entropy natin, specific entropy ng steam, since we have an irreversible process now. Okay? So interpolating from the steam table, T2 is now equal to 246.07 degrees Celsius, and S2 is now 7.50 kilojoules per kilogram Kelvin. So if papansin nyo, for the irreversible case of both a steam turbine and a compressor, okay, the irreversibility will always reduce to either an increase in the steam quality of the outlet or an increase in the temperature of the outlet conditions. Okay, for our last example, let us now consider the adiabatic expansion of air Okay, so 100 kilomoles of air is to be expanded adiabatically for upstream conditions of 500 Kelvin and 10 bar to the downstream pressure of 1.2 bar. If the turbine has an isentropic efficiency of 75%, calculate A, the downstream temperature, B, the turbine work in kilowatts, and C, the rate of entropy generation in kilowatts per Kelvin. Assume air to be an ideal gas now with a constant heat capacity of 3.5 R. So again, to start our calculations, always recall the definition of the isentropic efficiency, which is equal to, in this case for a turbine, H2 minus H1 over H2 prime minus H1. However, since we're working for ideal gas calculations, mas maganda na delta H is equal to Cp delta T. Okay, so kunin natin ngayon, Cp times T2 prime minus T1, this is equal to delta H isentropic, and Cp T2 minus T1, this is equal to delta H ng actual conditions natin. Okay, so to start calculations, let's calculate first the isentropic outlet temperature. And the entropy change for an ideal gas is given by as follows, assuming constant Cp. Okay, so pansin nyo, 0 is now equal to Cp ln T2 prime over T naught minus ln P over P naught, or in fact, pansin nyo, you will also reduce this to Tp raised to 1 minus gamma over gamma is equal to constant. Because in this case, we have a reversible adiabatic process for the ideal condition. So reversible adiabatic, isentropic din yun. Okay, so the Tp gamma relations will hold true, assuming again constant yung heat capacities. Okay. So using either of these two, okay, kasi pwede naman gamitin to kung again constant lang dapat sa Cp. Using that, T2 prime is now 272.82 Kelvin. Okay. And for the ideal work is just equal to delta H ideal, which is equal to Cp delta T ideal, which is Cp T2 minus T2 prime minus T1. So delta H prime is equal to Cp T2 prime minus T naught. Okay, since nakuha natin ngayon yung T2 prime or the temperature for the reversible case, let us now proceed to the actual case. So for us to do that, let us use the definition of the isentropic efficiency, which is delta H actual over delta H prime, which is now equal to 0.75. And we know that delta H prime is equal to Cp times T2 prime minus T naught. And the actual delta H is equal to Cp times T2 minus T naught. So substituting here, so thermal isentropic efficiency, which is equal to 0.75, is equal to the following expression. We can cancel Cp and obtain now the value of T2, which is 329.615 Kelvin. And you can now get delta H actual, which is negative 4958.03 kilojoules per kilomole. Okay, again, using ideal gas Cp, which is 3.5 R for air. And to get the actual work is just equal to delta H actual times the molar flow rate and dot. So making the necessary conversion, you will now get work is equal to negative 689 kilowatts. And last but not least, let us now calculate the total entropy change or the rate of entropy generation. Okay, so the rate of entropy change of our flow streams is equal to the following. For an ideal gas, okay, we can get the entropy change since we have already calculated the actual temperature outlet, and calculating the delta S of our flow stream is now equal to 5.50 kilojoules per kilomole Kelvin. So you can now get delta S m dot or delta S n dot since naka per mole tayo. The rate of entropy generation is simply equal to n dot times delta S. Wala tayong entropy change in surroundings since we have an adiabatic process. So we only have internal irreversibility but no external irreversibilities. Okay, so the rate of entropy generation is now equal to 0.7642 kilowatts per Kelvin. And that ends our discussion on the second law of thermodynamics, both for closed systems and open systems, as well as the mathematical statements of the second law of thermodynamics. Okay, our next topics for the next 3 weeks would now be the discussion of power cycles and refrigeration cycles and the first and second law analysis of these cycles. So if you have any questions regarding any of the past week's lecture, please contact me as soon as possible. Thank you.